understand about this subject even better. So let's begin. So let's begin with introduction to IoT. So IoT stands for Internet of Things, and this term comprises of a word internet, which we are very familiar with. So just for sake of understanding, what is internet? If we go with the definition, so internet is a global computer network that have data, communication facilities, information, and they are interconnected via communication protocols. See, right now I'm discussing about the internet, and now I will be discussing about the IoT. Now, what's IoT? Now, Internet of Things refers to the collective network of connected devices and the technology that facilitate the communication between the devices and the cloud, as well as between the devices themselves. Thanks to the inexpensive computer chips and the high bandwidth telecommunication, we have now billions of devices connected to the internet. See, the main motto to describe about the internet and IoT is to understand the difference between the two or the similarities between the two. If we discuss about the differences between the two, is that the IoT focuses over physical objects, whereas the internet it focuses on constituents like people, things, data, and processes. Simply put, Internet of Things involves interconnectivity of physical objects and data input and output, whereas Internet is a comprehensive term that refers to the interconnectivity of various technologies, processes, and people. Guys, are you able to understand this difference between the two? Hello.
Yes, sir.
Okay. If you have any doubt, then you can do ask. Huh? Okay. So now moving forward to the features of IoT. Now talking about the features of IoT, IoT has three main features that is connect, analyze, and integrate. Now, as the term suggests, connect means connecting various things over the IoT platform. Analyze means to analyze the data that is being collected to build a business intelligence, whereas integrate means to integrate various models to improve user experience. Now we will dive into each of this concept in even more to get even more better understanding of these. Now about connect. In connect, we have three major parts, that is device visualization, high speed messaging, and endpoint management. In device virtualization, I'm sorry. In device virtualization, it standardizes the integration of devices with the IoT enterprise. See, you do need to connect all the devices to your IoT network, right? So device virtualization means the integration of all the devices to the IoT enterprise, and for that you need some standardization. It can be in form of the same kind of technology to integrate over the network, or any other thing. Now high speed messaging. Now if you are connected to a network and you do need high speed messaging to send or receive your data to do various tasks, right? So high speed messaging is important. It enables reliable, secure, and bidirectional communication between the devices and the cloud. Now the third point is endpoint management. Now, managing device endpoint identity, metadata, and life cycle states for all the devices. Now, describe it in simple words. It's one in which devices which data is coming at what is needed to be done with the data as well. Okay, so means whatever data we are getting, it just describes the what data is coming, how to manage those data. So that comes under endpoint management. Guys, am I clear? Is there any doubt at this point? Hello. Okay.
So
So
can
as
you,
hello, yeah.
sir, can you tell endpoint management was like in brief?
Just can you type what you're saying? I'm not able to hear you well.
Hello, sir. Now am I audible now?
Yes, yes, you are.
Sir, I wanted to. Sir, can you explain that endpoint management was?
Endpoint management system. Yeah. See the endpoint management device. See, it basically manages the identity, metadata, and lifecycle stages. See, when you receive some data, hmm, So that data is achieved in a raw form, right? So there you need a management system to analyze that what kind of data is there, from where it has been fetched, and what to do with that data, right? So for this entire system there is endpoint management. Am I are you able to understand it now? Well,
Yes, sir. Yes, about it.
okay.
Thanks.
Okay, so now moving ahead, now next part is analyze. In analyze we again have three parts, that is stream processing, data enrichment, and event store. In stream processing, in that we have real-time analysis of the incoming data streams and with event aggregation, filtering, and correlations. Means whatever data you receive, that data is being analyzed, it is being aggregated, filtered, and correlated. Fine. In next part, that is data enrichment. In this we receive a lot of raw data, right, with contextual information. So in at this level we generate contextual information and generate composite streams. To break down it into simpler words, in this we identify the important information which is to be taken forward and has to be left behind, so that the computation can so that much more easier and faster computation can be achieved in later phases. Now next part, that is event store. It requires a visualization of massive amount of data with integrated cloud services support and enables big data analysis. Okay. So with this, we're done with analyze. Any doubt in analyze part? Hello. Yeah.
So can you explain the stream process again?
Yeah, stream process, yes. So the stream process is see when the data that comes. So in so stream process is typically the process in which the incoming data is being aggregated, filtered, and correlated. Means whatever data you are getting now, it has to be filtered, right? Because there are many noises and things like that. When you receive data from your sensors or from any source, there are many things that you don't need to be processed, right? So in stream processing, that thing is being done. So there it is being filtered, it is being aggregated, that okay, which data is from which source and what is to be done with what, and then they're correlated with their entire data set. Fine. Is it clear now?
Yes, sir.
Okay. Okay, so now moving forward to the third feature, that is integrate. Now again, integrate has three parts, that is enterprise connectivity, REST APIs, and command and control. Now enterprise connectivity, it dynamically dispatches critical IoT data and events to application and process flows. For example, if there is a leakage problem, then the IoT system will contact the corresponding service provider and corresponding details will be dispatched. Right. So that is your enterprise connectivity. Hmm? It basically dispatches your critical IoT data to the applications according to the process flow. Fine. The next is REST APIs. So this is just so REST APIs is just the way through which the communication is being done. So IoT we use API based integration with cloud apps and IoT devices. Now third part, that is command and control. In command and control it sends the messages to the devices from enterprise and the mobile apps independent of the device connectivity. Fine. So integrate. So I guess that integrate part is also clear now. Is there any doubt?
Yes.
Okay. Uh, so moving to the next part, that is IoT architecture. So first describing about what is architecture, why it is essential. In essence, an IoT architecture is a system of numerous elements that range from sensors, protocols, actuators to the cloud services and layers. Beside devices and sensors, the IoT architecture layer are distinguished to track the consistency of the system through which protocols and gateways processes. Okay. So IoT architecture, in simpler words, it can be described as a flowchart that how the entire process happens, fine, in our IoT system and things like that. So in that, the most basic one is a three-layer architecture. This is the most basic and widely accepted format of three-layer architecture. It was first introduced with the earliest research into the IoT had begun. Now, it has three layers: data, perception, network, and application. Now, just try to observe this diagram. This diagram briefly describes about the three layers. I will just give you a minute and just go through this diagram. You will almost, it is self-explanatory that what these layers are about. Then I will explain that. Okay. So see, uh, you need more time, or should I explain now? Hello? Hello?
Sir,
So you
समझा
may
दीजिए
explain
आप.
it.
Huh? Sorry?
So you may explain it.
Okay, fine, sure. Okay. So starting with, see, this bottom layer is the perception layer. This layer is the physical layer of the architecture. This is where all the sensors and connected device come into play. They gather various information from the environment, and that is needed for the project. These can be edge devices, sensors, and actuators that interact with the environment. Fine. Second is the network layer. Uh, the data that is collected from all these devices from the perception layer needs to be transmitted and processed, right? And that's the network layer's job. It connects these devices to other smart objects. Its object serves and network devices. It also handles the transmission of all the data. Now moving to the third layer, that is the application layer. Now, application layer is what the users interact with. It is what responsible for delivery of the application specific services to the user. That can be smart home implementation. For example, the user taps a button to on the app to operate a coughing machine. So that application or that button is the part of application layer. So this is the most basic layer that I have discussed. That is a three-layer model. Now let us proceed to the five-layer architecture. Now, five-layer architecture is somewhat that is most accepted one and is being used in the industry. Now, five-layer architecture has, of course, as the name suggests, it has five layers. It's perception layer, it has network or transportation layer, it has middle layer or processing layer, it has application layer and business layer. Okay. So let me describe each of this layer in detail now. Now, perception layer, as described in three-layer architecture, it's the same. Is the first layer of the IoT architecture. In the perspective layer, number of sensors and the actuators are used to gather the user's interface like temperature, moisture, their motion and things like that. The main function of this layer is to get information from the surrounding and pass it through the different layers. The next layer is the network layer. Similarly, as described before, the network layer, as the name suggests, it is the connecting layer between the perception and the middle layer. It gets data from the perception layer and passes data to the middle layer using the network technology. It can be 3G, 4G, Bluetooth, Wi-Fi, anything that is being made available to. This is called communication layer as well, because it is the one which is communicating between the perception and the middle layer. All the transfer of data is done securely, keeping the obtained data confidential. Okay, so till this point of time, has any one of you got any doubt? Hello?
No, sir.
Okay, fine, fine. Okay, so moving on to the third layer, that is middle layer or processing layer. So middle layer processing layer has some advantages, like it's about storage, computation, processing, action taking capabilities, etc. The main focus is it stores all the data sets, and based upon the device address and name, it gives the appropriate data to that device. It can also take decision based upon the calculation done through the data set obtained from the sensors. Okay, so that is the processing layer. See, if you would have noticed, the first two layers were similar to that of the three-layer architecture. This fourth layer is somewhat that is new. Huh? Sorry, this third layer is somewhat that is new, that is middle layer or the processing layer. Now moving on to the fourth layer, that is application layer. Again, this is similar to that what we have discussed before in three-layer architecture. The application layer is the layer that manages all the application process based upon the information obtained from the middle layer. The application involves sending emails, activating alarms, security systems, turn on or off a device, smartwatches, smart agriculture, etc. So now application layer, I guess, is clear because it is same as before. But still, if any one of you has got some doubt, then they can ask. Okay, so I'm moving ahead if there is no doubt. Okay, so the final layer, that is the business layer. This is again a new layer that is being added to the architecture in the five-layer architecture. See, for success of any device, it's not just important that what your technology is, but it is also important that how it is being delivered to the consumers, right? So business layer does that task for the device. It involves making flow charts, graphs, analyzing the results, and how to improve the devices. So when we are talking about industrialization using IoT and stuff, this business layer also become an important layer that is being emphasized at the industrial level as well. Fine. So with this, we are done with the architecture. If any one of you has got some doubts, then they can ask. Or I have a question for you guys. Can any one of you take some example and describe about all these layers? Anyone? Hello. Guys, if you have got some doubts, then also you can ask. Okay, in that case, moving forward. So this is the basic again flowchart that how IoT device, how the IoT system works, right? So collection of data, then the collected data and data transfer, and this analyzing data and action. This can be described as basic three-layer architecture. I've just put it to just give you guys a hint at how the things are being done. Now coming to two concepts, that is cloud and fog computing. I guess most of you would be aware about cloud computing, right? Can anyone of you tell that what is cloud computing and fog computing? Anyone? Hello?
Sir, cloud computing is when we can have remote access to a server and two people at very different locations can access that particular server.
Okay. What about fog? Anyone has some idea that what is fog computing? Okay. So I'll guess that no one is aware of that term. Okay, fine.
Sir,
We'll
it is
discuss.
more
Sorry?
widespread than cloud computing.
It is more
More widespread than.
widespread than I guess not. That's not the right explanation, but fine, fine, fine. That's good. That's good that you have at least tried. Anyone else? Okay. So now, what is cloud computing? Let's start from that. The delivery of on-demand computing service is known as cloud computing. We may use application to store process power over the internet without owning any computing infrastructure or data center. Anyone can rent access to anything from the application to store from a cloud service provider. It is pay as you go service, right? So in cloud computing, basically it's a computer that is far away and you can access it using internet. Fine. So our main focus here is that what is fog computing? Huh? So fog computing is a decentralized computing infrastructure or process in which the computing resource are located between the data source and cloud or another data center. Fog computing is a paradigm that provide services to the user to request on edge networks. Devices at fog layer typically perform networking related operations like routers, gateways, bridges, and hubs. The researchers envision these devices to perform both computational and networking tasks simultaneously. Although these tools are research constrained, compared to the cloud services, the geological spread of the decentralized network help to provide reliable services with coverage of over a wide area. Fog is a physical location of the computing device which is much closer to the user. So I guess with this explanation, you would have got the basic understanding that what is fog computing. Huh? Now, with an example, I will explain that what is difference between the two. Huh? So, for example, if there is smart street light system, huh? So at times you may need that entire computation is taking place and everything is taking place. But what the drawback of cloud computing is that the lag time between the sending and receiving the data is much higher, huh? And that lag time can sometimes be not that favorable. And in those conditions, we use fog computing. Fog computing provides you the on-edge computational power. Means at that particular location, the entire computation can be done with the all the data that has been received. Uh, Now, to give a more comparative study between the two, here is the chart which is comparing the two, that is cloud computing and fog computing. As I said, if you compare delay, so cloud computing has higher latency as compared to that of fog computing. Talking about capacity, cloud computing has got really high capacities as compared to fog computing. Talking about responsiveness, the response time of cloud computing is low as I described before. Talking about security, fog computing has high security. Cloud computing has less security as compared to fog computing. Now, speed, data integration, mobility, location awareness, these all are the things again that have been described. So these are the things that one do need to keep in point when he's designing his this entire IoT architecture and things like those. That what to keep where. Uh, so I will just add up one. Yeah. Any doubt? Hello. Hello, guys. Is there any doubt? No. Okay.
Yes.
Fine. I will just add one more thing. Uh, just a sec. Yeah. If you talk about the architecture of the cloud computing, so as described before, as there are two layers, right? There is transport layer and physical layer. Transportation layer is just this communication layer, and physical layer is your perception layer. So it happens in between the transport and physical layer. As described before, this fog computing happens at edge of the computation. Means it happens at the place where the entire IoT system is, right? So it has monitoring layer, pre-processing layer, storage layer, and security layer. Now monitoring, pre-processing, storage, and security are being same as being described before. And the name themselves describes them well, right? Monitoring means it monitors the data, it pre-processes the data, then storage is responsible for storing the data, and then security data. And many times it has been seen that in many big infrastructures, this IoT based architectures, the fog computing and cloud computing happens in a series fashion. That which operations need to be done on the priority basis that have been done on fog computing, and the rest have been pushed to the cloud computing. Fine. And with this, I conclude. I conclude with my part. Uh, Aditya.
Yeah. Do you have any questions related to the last part? Anyone?
Yeah. Guys, any doubts related to architectures according to fog, cloud computing, anything? Okay. Okay, so I'm stop sharing. Huh?
Yeah, fine.
Just a second, Aditya. Just wait for a second.
Yeah, so is my screen visible to everybody?
Yes, sir. Yes, sir.
So embedded systems. Anyone got any idea like what they are or anything? No one. Fine. I start with my presentation. So, an embedded system is a computer system, a combination of a computer processor, computer memory, and peripheral devices that has a dedicated function with a larger mechanical or electronic system. It is embedded as a part of a complete device, often including electrical or electronic hardware and mechanical parts. Since it controls physical operations of the system it is a part of, the embedded systems often have real-time computing constraints. The processors used can range from general purpose to those specialized in a certain class of computations or even custom designed for the application at hand. Since embedded systems is since the embedded system is dedicated to a specific task, design engineers usually optimize it to reduce the size and cost of the product and increase the reliability and performance. Some embedded systems are mass produced, benefiting from the economies of scale. That means that they may be available at a very low cost. Embedded systems are designed to do some specific tasks rather than be a general purpose computer for multiple tasks. Some also have real-time performance constraints that must be met for reasons such as safety and usability, while others may have low or no performance requirements at all, allowing the system hardware to be simplified to reduce costs. Embedded systems are not always standalone devices. Many embedded systems consist of small parts within a larger device that serves a more general purpose. For example, the stereo system inside an automobile provides a specific function as a subsystem of the car itself. The programs written for embedded systems are referred to as firmware and are stored in read-only memory or flash memory chips. They run with limited computer hardware resources, little memory, and generally do not depend on human interaction for input, thus eliminating the necessity of a user interface. However, we may require some applications wherein we need complex graphical user interfaces that resemble modern computer desktop operating systems, like an ATM machine, for example. Simple embedded systems use buttons, LEDs, and graphical character LCD displays with a simple menu, whereas more sophisticated devices may use a graphical screen with touch sensing or screen at soft keys, providing flexibility while minimizing space used. Uh, some systems provide a user interface remotely with the help of a serial or a network connection. This approach avoids the cost of a display, simplifies the board support package, which is basically the device drivers that that are needed for supporting the board, and allows designers to build a rich user interface on the PC. A good example of this is the web page provided for a router. It is the router's configuration program and requires a user interface, but instead of having a hardware UI built into the router itself, it uses a web browser on the computer connected to the network. So, any doubts till now? Okay, fine. So, a system on a chip. A system on a chip is basically a complete system inside a single chip. It consists of multiple processors, caches, and different types of memories, and commonly various peripherals like interfaces for wired or wireless communication on a single chip. Often, graphics processing units and digital signal processors include such chips. SOCs can be implemented as an application specific integrated circuit, also called an ASIC, or using a field programmable gate array FPGA, which typically can be reconfigured. The difference between an ASIC and an FPGA can be understood as ASICs being the equivalent of a soldered circuit board and the FPGA being the equivalent of a breadboard. The difference being that FPGAs can be reprogrammed, whereas ASICs are frozen once made and the design cannot be changed. FPGAs are typically used for prototyping or for low production volumes, whereas ASICs are used for mass production. ASIC implementations are common for very high volume embedded systems like mobile phones and smartphones. ASIC or FPGA implementations may be used for not so high volume embedded systems with special needs like in avionics. Now we move on to the software used in embedded systems. So these are called embedded software. Embedded softwares may or may not always be always using an operating system. Software includes device drivers for all the specific hardware it has to work with, and this constitutes the board support package. Various architectures are used to design embedded softwares, ranging from a simple control loop, wherein the software simply has a loop monitoring the inputs and generates responses to them, to complex designs using large operating system kernels, providing an environment similar to a desktop operating system. In a simple control loop design, the software simply has a loop which monitors the input device and executes the corresponding subroutines, only if there is a new action on the input device. The loop calls subroutines, each of which manages a part of the hardware or software. Hence, it is called a simple control loop. The inter-control loops, control systems are, as the name suggests, predominantly controlled by interrupts. This means that tasks performed by the system are triggered by different kinds of events, like an interrupt generated by a timer in a predefined frequency, or when a serial port controller receives a byte. These kinds of systems are used if event handlers need low latency and event handlers are short and simple. Sometimes the interrupt handler will add longer tasks to a queue structure. Later, after the interrupt handler has finished, these tasks are executed by the main loop itself. This method brings the system close to a multitasking kernel with discrete processes. A cooperative multitasking system, also called a non-preemptive multitasking system, is very similar to the simple control loop scheme, except that the loop is hidden inside an API. The programmer defines a series of tasks, and each task gets its own environment to run in. When a task is idle, it calls an idle routine. The operating system never actually initiates a context switch, but the processes voluntarily yield control periodically or when idle or logically blocked. It is called cooperative because a task needs to cooperate with each other for the scheduling scheme to work. In a preemptive multitasking system is basically a multi-threading system. A low-level piece of code switches between tasks or threads based on a timer which may be connected to an interrupt. This is the level at which the system is generally considered to have an operating system kernel. Depending on how much functionality is required, it introduces more or less of the complexities of managing multiple tasks running conceptually in parallel. So this image describes the difference between a preemptive and non-preemptive scheme. In a preemptive scheme, it's a timer that initiates this switch, and like each process gets a specific time period for working on the CPU. Whereas in a non-preemptive scheme, the switch is made only when this process calls an idle routine. Now, a microkernel is a logical step up from a real-time operating system. It is the near minimum amount of software that can provide mechanisms to implement an operating system. These mechanisms include low-level address space management, thread management, and inter-process communication. The usual arrangement is that the operating system kernel allocates memory and switches the CPU to different threads of execution. In an exokernel, the exokernel kernel communicates efficiently by normal subroutine calls. The operating system generally represents hardware resources to the application through high-level abstractions such as file systems. The implemented abstractions are called libraries. The software can interact with the hardware much more directly this way, and the kernel just ensures that the requested resource is free and the application is allowed to access it. The hardware and all the software in the system are available to and extensible by application programmers. In a monolithic kernel system, a relatively large kernel with sophisticated capabilities is adapted to suit an embedded environment. This gives programmers an environment similar to a desktop operating system like Linux or Microsoft Windows, and is therefore very productive for development. But on the downside, it requires considerably more hardware resources, is often more expensive, and because of the complexity of these kernels, it can be less predictable. Despite the increased cost in hardware, this type of embedded system is increasing in popularity, especially on more powerful embedded devices such as wireless routers and GPS navigation system. This is because these systems provide ports to common embedded chipsets and permit the reuse of publicly available code for device drivers and web servers. And the development, it provides a designer the choice to have a broader feature set in the beginning and then trim the distribution according to which functionalities are needed and which are not to save memory. Applications of embedded systems can be found all around you. They are commonly found in consumer electronics and industrial and automotive subsystems. Telecommunication systems employ numerous embedded systems from telephone switches to cell phones at the end user. Computer networking uses dedicated routers and network bridges to route data. Household appliances such as microwave ovens, washing machines, and dishwashers are mostly ASIC based. Uh, Home automation also uses a wired and wireless networking that can be used to control lights, security, audiovisual surveillance, etc. All of which use various embedded devices for sensing and controlling. So, with this, I end this topic now. Like, if you have any doubts.
Guys, we are open to doubts for any of the part that you that was discussed today.
The difference between ASICs and FPGAs. You can think of ASIC as once you've designed and once you have synthesized an ASIC, like once you've produced it as in the hardware, then you cannot actually change the internal circuits afterwards. But in an FPGA, you can just think of an FPGA like a mini breadboard. It has if you go into the internal structure, it has logic blocks and it's basically a gate array as the name suggests. So it has logical blocks. So those blocks can be programmed and reprogrammed afterwards. There are various methods for reprogramming, and you can actually write a new logic into the same chip. Like the same chip can can function as it's basically reprogrammable. Like the internal circuit, you can change it again and again. Does that clear it out? Okay.
Okay, any other doubts? हाँ PPTs मिल जाएंगे. Hmm.
Bye, sir. Bye, see you.
Bye, sir.
Bye, bye.
Hi, guys.
Bye, sir.
Bye, sir. Thank you, sir. Bye, sir.
Bye, sir.
Bye,
Bye.
sir. Good night, sir. Nice seniors.
Bye, bye.